Hello, Algebra 2A, and welcome to Unit 2 in our distance learning Algebra 2A. We are going to move into a trigonometry unit, and we are starting with the Pythagorean Theorem and distance formula. So our goal today is to use the Pythagorean Theorem and its inverse, and then develop the distance formula from the Pythagorean Theorem. Let's take a look first at some new concepts, or hopefully some old concepts that are just reminders. A right triangle we've learned is a triangle with one right angle. The legs are the two sides that will form the right angle, and the hypotenuse is the third and longest side. For the Pythagorean theorem, we are going to use the variable a and b for the legs, and then c is going to be reserved for the hypotenuse. So our Pythagorean theorem states that in a right triangle, the sum of the squares of the legs equals the square of the length of the hypotenuse. For legs a, b, and c and hypotenuse c, a squared plus b squared equals c squared. So this is probably the most popular formula in mathematics, and there's a lot of different variations. We'll find out in a bit. The distance formula is a variation of the Pythagorean theorem, but it does just basically drive everything that you see in trigonometry. The converse of the Pythagorean theorem is used when we don't know if a triangle is a right triangle or not. So it says that the sum of the squares of the lengths of the two shorter sides of a triangle equals the square of the length of the longest side. Then we know for sure that it is a right triangle. So sometimes we're given three measures and we're not sure if it's a right triangle. Well, here's an easy way to check. This can also be used in construction or architecture to check to see if you have measurements equaling 90 degrees. As we look at example 1, it asks us to take the sides of a triangle 9, 40, and 41 and check to see if it's a right triangle. By looking at the lengths, right away we have to designate 41 will be our hypotenuse, and then 9 and 40, doesn't matter which one of those two you want to make the legs, A or B, you could use them in any order. So we'll take and check with the Pythagorean theorem. We'll check, does 9 squared plus 40 squared, does that equal 41 squared? So we put a little question mark there. On the left side, 9 squared is going to equal to 81, and then 40 squared is 1600, so that's 1681. And then 41 squared is also equal to 1681. So this one does check. That will form a right triangle. In problem 2, we're given the lengths 20, 21, and 25. So again, we will designate 25 since it is the longest. That would have to be the hypotenuse if this is a right triangle. Remember, we don't know that yet. So we'll take 20 squared plus 21 squared and ask, does that equal 25 squared? 20 squared is equal to 400, and then 21 squared is 441, so the left side is going to equal 841. On our right side, 25 times 25 is 625. And looking, obviously, 841, 625, they are not equal. So this is a triangle, but it's not going to form a right triangle. In problem 2, we'll use the Pythagorean theorem to find missing values. So in right triangles, if you know two sides but not the third side, you can always use the Pythagorean theorem to find the missing side. So as we look at our triangle, the first thing we're going to want to identify is the legs. You have a leg A, you have a leg B, and then you have the hypotenuse C. So I can tell this is my hypotenuse that's directly opposite the 90-degree angle, which makes it my hypotenuse. So we'll fill in what we know about the triangle into the Pythagorean theorem. So we'll take 36 squared plus x squared needs to equal 85 squared. Taking 36 squared will give us 1296, and taking 85 squared will give us 7225. We will have to do a little algebra to get x squared alone, so we'll subtract the 1296 over from our hypotenuse squared, and ends up giving us x squared is equal to 5929. Now we have to think about algebra. Algebra is inverse operations, and what is the inverse of a square? That will be a square root. So our last step is to square root both sides. When we square root, we get a nice perfect square of 77. So there's our missing leg on that right triangle. Heading over to part B on example 2, we have a triangle presented on a coordinate plane, and this is a problem I could see on an ACT test where it's checking whether you know a couple of different math concepts. You might look at this one right away and go, oh yeah, this one's pretty easy, I could solve this one pretty quick. But if you look carefully on the y-axis as we count squares, we have 2 squares to get up to that first marking of 2, which tells us that they're counting by ones on the y-axis. But then if you look at the x-axis, it goes from 2 to 4, so that tells us that they are counting by 2s. It's kind of hard to see on that blue background, but that y is what we're solving for. So we are solving for the hypotenuse because that is the longest side of this right triangle. To use the Pythagorean theorem with the right triangle, we do need to know 2 of the sides. So take a second and think, how could you figure out the 2 legs of this right triangle? You can pause the video and try it yourself. Well, on my horizontal leg, I would count the squares. I've got 1, 2, 3, 4, 5, 6. Since my scale is counting by 2, that means the length of this leg is 12 units. On my vertical axis, I've got 1, 2, 3, 4, 5 squares, and each square represents 1, so I've got a total of 5 units, which is all I need to know to use the Pythagorean theorem, because if I know 2 sides of a right triangle, I can find the third side. So we start to work through our Pythagorean theorem. We take 5 squared, which is 25, and then we take 12 squared, which is 144. That'll give us 169 equals y squared, and just like we did before, the inverse of squaring a number is taking the root. So we'll get 13 is equal to y. And remember, you can always pause the video if you need to catch up on any of the steps that we're doing, or you can always rewind to rewatch things at any time. Lastly, we are going to develop the distance formula from the Pythagorean theorem, and we're going to do that by looking back at that last problem. In the last problem, we were trying to find the length of that green line, which could represent any diagonal line on the coordinate plane. When you have a diagonal on the coordinate plane, you can connect a horizontal and vertical to always create a right triangle. Now as you look at the coordinates of the endpoints of the green line, we have the upper left coordinate is -6, 3, and the lower right coordinate is 6, -2. I want you to first look at the x-coordinates. So the x-coordinate of -6 and the x-coordinate of 6. The horizontal span will be the distance from -6 to 6. So take a moment, pause the video. What's the distance from -6 to 6? That is 12, which is what we got when we counted that distance. Now you may have subtracted those numbers. You may have counted -6 to 6 as 6 units to get to 0, another 6 units to get to 6. But in either case, you can use some type of subtraction to find that distance. Next, look at the y-coordinates. What's the distance from the upper left y-coordinate 3 to the lower right endpoint y-coordinate -2? That is correct. That is 5. Would be that vertical distance from 3 to -2. In order to develop the legs, we took in the horizontal case to get this 12, we just took the two x coordinates and subtracted them. To find the length of the vertical leg, we took the two y coordinates and subtracted them. Once we subtracted the coordinates, we went over to here and we squared the difference of those y coordinates, we squared the difference of those x coordinates, and we started to develop the Pythagorean theorem. So far then, we've developed that we can take any diagonal line, we can take the x coordinates, subtract them, and y coordinates, subtract them, to start to find the two legs, the horizontal and vertical leg, that would connect the endpoints of that diagonal line. Now going back to our last problem, and whenever we do the Pythagorean theorem, once we get the sum of the squares of those legs, our last step is always going to be to square root. So in our distance formula, we'll need to account that when we are finding the hypotenuse c, which is c squared, we still have to root our sum of our two legs. In example 3, we're going to find the distance of a segment with endpoints at -2, 8 and 6, -7 by using the distance formula. So we just talked about that any diagonal line you can connect with a horizontal and a vertical to make a right triangle, and simply just subtracting the x coordinates, subtracting the y coordinates, we'll start to find those distances. And then we did a little variation of the Pythagorean theorem to start to find the length of that diagonal. So I like to organize our coordinates. We got x1, y1, x2, y2, and then we can start to put them into the distance formula above. So we've got 6, which is my second x coordinate, minus -2 squared plus -7 minus 8 squared. Now it's just down to doing some arithmetic to solve this out. 6 minus -2 squared is 8. -7 minus 8 is -15 squared. Continue simplifying. 8 squared to be 64, and be careful on -15 squared. Even though that's -15, when you square a number, times it by itself, negative times a negative is a positive. So we'd have square root of 64 plus 225. Keep simplifying. 64 plus 225 is 289. The square root of 289 is going to give us a perfect square answer, 17. In example 2, we're given two endpoints of a diagonal again, so we'll use our distance formula. Our x's, 6 minus -4 squared, is going to give us 10. So when we're subtracting a negative, we're really adding. And then 5 minus a -1 squared will give us 6. Continuing to solve, we'll get the square root of 100 plus 36, and we get the square root of 136. Now if you know your perfect squares, 121 is a perfect square, and then 144, which makes 136 not a perfect square, so we will use our calculator and round to the nearest tenth. And we get 11.66, which will round the 6 back up to 11.7 units. Now maybe you noticed when I did the 6 minus -4, now maybe you noticed, but when I did the 6 minus -4, 6 I designated as x1, -4 as x2. Just wanted to remind you that it does not matter in the distance formula which way you subtract, because anytime you square your number in the Pythagorean theorem, it'll always come back to positive. here's kind of an overview of what we did in Unit 2 trigonometry, the Pythagorean Theorem. So if you want to pause it here and just kind of look over everything, there it all is. Thanks for joining me. This has been Mr. Rengel signing off, and hope to see you soon. Goodbye.